Okay, well now we're ready to check out the equipment and make sure that everything is working. Okay? First step is to put the down conversion crystal back into the system. So I'm going to take it out of the desiccator. Carefully, remember handling it only by the base. And bring this over. Set it into the system again, carefully. Okay? And then now we can turn off the lights, turn on the photon counter, turn on the laser, and try the experiment. So we'll turn off the room lights, turn on the safe lights. I'm going to put on my glasses and start the laser. And finally, we'll start the avalanche photodiodes, turn those on. And now we'll start photon counter. Clear the display here. There we are. Very good. And we're getting count rates now, which are quite acceptable, on the order of 10 to 20,000 per second. By the way, these are single photon counts because the FPGA should be in the single photon counting mode. That is, switch 0 should be on, and all the other switches should be off. Okay, so now, if you've gotten this far, you know that the equipment is basically working. The next thing you should do is to check the entangled pair count rates. So now we're going to switch the FPGA. We'll turn switch 0 off. We'll turn switch 2 on. And let me clear the chart here. And now we're measuring entangled counts. And notice something. At the moment, one of the signals, the red trace, that corresponds to the gate transmit coincidences, is high, and all the others are low. That's a little bit different than what we saw last time, and it's because we have now the polarizing beam splitter on the gate path. So now we can only see coincidences between gate and transmit because entangled pairs that would go to reflect wouldn't get past the beam splitter on the gate side. Okay, in any event, that is what we see. Now, okay, so things look good. Let's stop for 1 second. Okay, just to go over this again. At the moment, we're seeing entangled pairs, but because of these polarizing beam splitters, we're only seeing entangled pairs where the polarization of the gate and signal photon have been measured to be vertical by these polarizing beam splitters, okay? So if you like, we're only sensitive to the vertical component of the down converted beams. The way this is set up, we should actually have equal vertical and horizontal components. Let's go check to see if we have a horizontal component as well. And the easiest way to do that is to use these two polarization rotators to rotate each one by 45 degrees so that the horizontal component of this light will be switched to be vertical and then go through our electrons just like before. So let's try that, okay? Now, you might not have this problem, but I have the problem that I can't see the indicators here unless I turn on a light. I'm going to use my phone and also put on some glasses. That's how it is, you know. Enjoy yourself while you're young. Okay, now let's switch this to 45 degrees. We'll likewise switch this one to 45 degrees. There we go. And now we can continue. I have to restart photon counter. It looks great. We're seeing exactly what we saw before, and the count rates are also similar. So that means that we have roughly equal, that the horizontal component of the signal here is roughly equal to the vertical component, okay? Which is just what we want. Now there's one more thing we need to check for. We want not only to have equal electric field magnitudes, if you like, in the vertical component and horizontal component coming from the crystal, we also want them to be in phase. We want this beam to be linearly polarized.